The next question asks us to state that the data, why they do not support the hypothesis. They're already telling us that the data does not support the hypothesis. But the question is why. The hypothesis that T equals K over H requires that a graph of T versus 1 over H will produce a straight line that's constant slope that passes through the data with error bars and passes through the origin. So what we've just done is laid out the premise. These are the scientific principles by which we would judge whether this is supporting the hypothesis. Now we move into observation mode. The observation we would make is the straight line that passes through the points does not and cannot be made to pass through the origin. Therefore, the data do not support the hypothesis. So again, we have our scientific principles and premises by which this would be judged. The observation about whether or not that occurs, and then the concluding statement tying the two together. That's how we hit it home. The next question, part B, starts right off with another equation. What we will do then is take that equation down below where we can really work it over. T equals K times the square root of 1 over H. Fitting this to the equation of a line, y equals mx plus b. Y-axis would be t. The slope would be k over m. The x-axis would be the square root of 1 over h. And again, we see there is no y-intercept, so it would be 0. Testing whether whether or not the data support it, a graph of t squared versus 1 over h. That's not what we did, but we can see why they did it that way. Typically, when we want to get rid of a radical, we square both sides. Doing so gives us t squared is k squared times 1 over h. Then comparing that to y equals mx plus b, we land at y-axis of t squared. The slope is k squared, and the x-axis is 1 over h. We see a y-axis of t squared. We see an x-axis of 1 over h, so we know the slope of this line would give us k squared. And there's a best fit line already drawn for us. That's nice, and we see that there is an error bar drawn there. Extremely large error bar, I might add. And it's our time to do our oizerga. The origin, 0, 0. And we see the line going through it. So this holds. So that's a check. That's doing what we expect it to do. And we see we are again in quadrant 1. The y-axis is time squared and second squared. And since we see between, say, 1 and 1.5, there are 10 marks. For 0.5, that means it must go by 0.05. 0.5, 1.0, or 0.1, 0.15, 0.2, 0.25, 0.3, 0.35, 0.4, 0.45, 0.5. So we have that scale down. X-axis, 1 over h, has units of per meter. And we see from 0 to 1, there are 1, 2, 3, 4, 5 increments. So this goes by 0.2. The intercept, we already know there's a y-intercept of 0, 0. We can read t squared and 1 over h. So any questions about those, we know just we'll read it off the graph. The slope is t squared over 1 over h, which is t squared h. That has units of second squared per meter, which we recognize as being meters per second squared inverted. So just like the previous graph, the slope might have given us 1 over the velocity. In this case, the slope might give us 1 over the acceleration. The area, t squared times 1 over h, is second squared. I made a mistake there. Hold on. That's not the units. I did that too quickly. Just jumping ahead of myself. The slope is t squared times h, so that's going to be second squared times meters, second squared meters, which has nothing, no significance that we're aware of. And the area, t squared times 1 over h, would be second squared per meter, which we recognize as similar to meters per second squared. It's the inverse. So this might be equal to 1 over the acceleration, perhaps. So that is the work we have done so far on part B in analyzing the graph.